Okay, I'd like to go through the definitions from the chapter on Riemann integration. Um, the chapter starts with the definition of least upper bound, and it's going to refer to both these definitions of a first point to the right and a rightmost point. So let's recall how those work. Um, if I take some kind of point set, and they don't have to be intervals, okay? They can be any point set you want. So let's say 0, 1, union 2, 3 as an example. If I draw this set, I would have, here's 0, here's 1, then I have some kind of gap, and then here's 2, and here's 3. Usually we use a shaded in circle to indicate that the point's in the set, and an open circle to indicate it's not in the set. And this set has a rightmost point. Okay. Let me move that over. Has a rightmost point. Now, that's this definition. It means that there's a point in the set, and no point of the set is bigger. Okay. So that's a rightmost point. If we modified this definition a little bit, and we looked at the point set, 2, 3, open, then, okay, I'd still have this piece the same, 0, 1. I'd start at 2, but then I'd end at 3, and having that be open. And that 3 is the first point to the right of this point set. Okay. Now, the only difference between these two sets is, that the right-hand side is either open or closed, and so it seems like that 3 is, the fact that it's 3 is the most important thing here. So this goes to the definition on page 13 of a least upper bound. So they say we've already shown that if M is a bounded point set, then it has a rightmost, or there's a first point to the right. That was the completeness axiom. We shall call this number the least upper bound. Okay, so maybe call this example 2 and example 1. In example 1, let's call it maybe M1, and let's call this M2. We have that the least upper bound of M1 is 3, and we have the least upper bound of M2 is 3. Now, this means that this concept unifies these two definitions. The word I'm more used to for this concept is called supremum, and we would just write SUP of M1 for that instead. I may slip up and use supremum sometimes when I'm speaking. I'm just referring to least upper bound. Everyone knows these two words for the same concept. It just depends on what book you learned out of, which word you default to. Now, the next definition is the greatest lower bound, I should say. And if you think about least upper bound, by the way, you're essentially looking at all the upper bounds of the set. So upper bounds of this set. 4 is an upper bound, 5 is an upper bound, 3.5 is an upper bound, and so on. And you're finding the smallest of those red points, the minimum. Maybe the minimum, maybe not. In the case of a first point to the right, it is the minimum. But in the case here, it would not be the minimum of the reds. There is no minimum. There is no smallest red point, no smallest upper bound. But 3 is an upper bound, I guess. So it would be the smallest of all upper bounds of that set. So some analysis books start off telling you about least upper bound and supremum. But this book's approach was to kind of make it now. Because at this point, we finally need this concept. Now, the corresponding notion is the greatest lower bound. Maybe if I modify M2 a little bit and make that a closed at 0, we can look at greatest lower bound. So in this case, this is the first point to the left. Is that appearing? Yes. To the left of M1 is 0. And then this would be the leftmost point. Again, it's very similar to rightmost and first point to the left, to the right, I mean. And again, they're the same because the only difference is that this was included in the set and this was not included in the set. And so we have this other notion of the greatest lower bound of the set of M1 is 0, and the greatest lower bound of M2 is also 0. Now, the other word for this is infimum, and people write INF for this concept. For those of you going on to graduate school or something, you'll probably see supremum and infimum. It seems to me to be the more common among people that do analysis, but your mileage may vary depending on what books you use. Now, in the problem sets, I did not give anyone problems, so I will do these problems and upload the videos for your benefit, but I won't do that here. I just want to focus on definitions in this current video. Now, we need to talk about what it means for a function to be bounded. So we had earlier a point set M is bounded means, I use BDD for bounded, means that there exists an A and a B such that M is a subset of AB. That is, you can put this set M into some interval. Okay. Now, what we want to do now is talk about what it means for a function to be bounded, and it just means its range is bounded. So, if I had a function like the sine function, it does some wiggly thing, right? This function, the range of the function is on the y-axis here, and it's between -1 and 1. So that range, the clouds are changing my light. I don't have no professional setup here. I'm at the will of the sun here. But the range of f, if this is f, the range of f is a subset of -1, 1. In fact, it's equal to -1, 1 in this case, but we could say it's also a subset of -2, 2, and that would still mean it's bounded. As opposed to, so that's sine. If I look instead at, say, the graph of tangent, it has this asymptote here, like this. In this case, the range of f is the entire real line. And so you cannot fit that into an interval. The way the book defines intervals is they don't allow a and b to be infinite. Now, there are situations that do allow that. For example, analysis as done in this book works in the what's called the extended real line, and that's important for say a measure theory class. But we're not a measure theory class. If we're lucky, we'll get to talk about measure a little bit at the end, but probably not. So we're only allowing these intervals as being, finite intervals. Okay, so that's the notion of a bounded function, and supremum and infimum. So I want to go through and now talk about the definition of these Riemann sums. Then this is very similar to what you did in Calc 1. Okay, so let me remind you what you did in Calc 1. Likely, okay, your mileage may vary exactly who you had or whatever, but generally speaking, in Calc 1, you think about a function, and then you start at an A, you go to a B, and then you sort of equally space the domain in some way, and then they start talking about, well, there's a left endpoint Riemann sum where you always take the left endpoint of the rectangles, and then those rectangles are defining your heights. And so you draw these little rectangles in. Okay, fine, yes. You may have had a right endpoint rectangle at some point, but the Riemann sum would be say, you need to add up. Usually you call this like x0, and then you say x1, x2, and so on. Maybe we should use t instead to be consistent with what the book does. And then this ends at some tn, and you say, well, I'm going to add up the areas of all these rectangles. Well, the width of the rectangle, these were all chosen to be some width delta t. In Calc 1, usually you split the interval into equally spaced subintervals. So you would have some kind of sum from 0 to n of the width of these things let's say k plus 1 minus tk, some kind of forward difference, times the value of the function, and in this case it would be at the left endpoint, so at tk. Now that would be this is the width, and this is the height of the function, and so by multiplying those, we end up with the area of each one of these little rectangles, and then we add them up to get an approximation of the area under the curve. Now, in analysis, this thing is still kind of how we're thinking about it, except we approach it a little more formally. We approach it in a little more nuanced way, as we have, the whole semester, right? So, this first thing we need is the notion of a partition. Now, a partition, these values of t that we've picked is an example of a partition, but partitions allow something more general. So if I have some interval from a to b, then a partition is just any choice of values. So maybe I pick t0 here, pick t1 here, maybe I pick t2 over here, t3 here, and then maybe this is t4. And that's a partition, okay? If you look at the definition, it says that a partition is a set of points, some finite number of points, satisfying that they're all sort of in order. So, if the subscripts are smaller, then it's further to the left. And the first one is the left endpoint, and the last one is the right endpoint. So that's one partition I could take. I can take all kinds of partitions. So I could take another partition, let's maybe use V or something, or W instead for the values. So maybe that's W0, maybe here's W1, here's W2, here's W3, here's W4, here's W5, and then here's W6. So that's another partition I could take. And you can kind of appreciate that there's going to be a lot of options for partitions. So that's the first thing to get a handle on, is the notion of a partition of an interval, and it's just a matter of picking some finite number of points with the property that they're ordered. So you pick them sort of in increasing order. The first one is the left endpoint of the interval, the last one's the right endpoint of the interval, and you only have finitely many of them. So we're not allowing an infinite sequence to be considered as part of this word partition. Now, that's partition. Now, we say that this definition of a Riemann sum, some number s. Now the s is this, this sum here. This is going to be our s, so to speak. S for sum. S for sum. So once I have a partition, I have to then pick my rectangles. So how are they picking the rectangles? Well, they just say, you have to pick some x's that are going to be the domain values of your rectangles. So let me get a new sheet of paper. We'll draw a function, and we will look at these various definitions. Because you see there's Riemann sum, and then there's upper Riemann sum, and then on the next page there's lower Riemann sum. So I want to sort of draw all three at once, if I can. So hopefully this doesn't end up too messy, but let's make a big old function. Big old graph of a function. Is this tall enough here? Yeah. Big old graph of a function. We'll make it a little wiggly in the middle. So maybe, this function, does this. It goes like that. Okay, so there's some function that I've drawn. It's continuous. It's pretty well behaved. Now, I want to look at, first off, this notion of an upper Riemann, a regular Riemann sum. So the number s is called a Riemann sum if there is a partition and a sequence of values such that each of those values is in the interval determined by the partitions, and s is this, this sum that we had earlier. Now, they're starting their sum at 1. I started mine earlier at 0. These are the exact same sum, okay? It's just reindexed, so don't worry about the formula so much. Just worry about the idea here. So if if this is my a, so this is a f of a, so this is a, and this domain value here is b at the right endpoint. Let me make sure all that's appearing on the screen okay. Yeah. Then I can make a partition. So let me just make a partition. Here's T0, I don't know, here's T1, here's T2, you know, here's T3, and let's say B is T4. So I have a partition consisting of 5 elements of the set. And for the first definition of a Riemann sum, I have to pick x values, and it can be anything in these intervals. So x1 has to live in T1 minus 1, or in other words, T0 to T1. So x1 has to live somewhere in here. And as far as Riemann sum's concerned, it doesn't care which value you pick. So I don't know, let's pick, I don't know, this one. That's x1, we're going to say. So x1, you know, maps to this point here. Okay? So this is, well, this is x1, f of x1. That's that coordinate. Okay? And then I have to pick one of these points in the remaining 3. So maybe here I pick x2 over here. Maybe I pick x3, I don't know, right here. And I pick x4, you know, maybe right here. Now this point maps up to this point maps up to here, and this point, let's see, it maps maybe to right there. Now, if you look at the rest of this definition, what they say is I take f of xi times this quantity. Now this quantity is the width of that. So of that subinterval determined by the partition. So this first bit of the partition between here and here, that's going to be one of my rectangle's bases. The next one is going to be here, and then in here, and then the next one's in here, and the last one is in here. So those are the bases of my rectangles. The heights of my rectangles are determined by the x values I picked. So this first one, the height is given by this value. I'm not taking a left Riemann sum or a right Riemann sum or anything like that. I'm taking one based at my x's. So if I draw the rectangle in here, going on with this, I end up with, you know, this rectangle. Now at this point, the height is given by this value. So okay, I get this rectangle here. And it goes until I reach the domain value T2 horizontally. So one thing that's different in real analysis in general from Calc 1 is that the width of these rectangles are not the same. Okay, there's nothing requiring them to be the same in the definition we have. It's just a convenient thing in Calc 1 for, you know, low-level freshman, sophomore, math people to, you know, pick something simple to construct. The next interval is this wide, and it's going to start at this height determined by x3. So we go across, we go up, and we'll get this rectangle here, no problem. And then the final one is at the height determined by this x4. Now, I pick those x's sort of arbitrarily. You could always pick left endpoints. There's nothing wrong with that. Okay, that's an equally valid Riemann sum. It'll determine an equally valid Riemann sum. And so when I add up the areas of these rectangles, then I get the number s, and that's the end of the story. Now, that's Riemann sum. Now, I have lots of options to pick any x in here that I want. So the height of this rectangle could be as low as this, or as tall as this point or this point. Or, you know, this one could be as tall as this, or as low as this rectangle. So there's lots of wiggle room there. The upper Riemann sum and the lower Riemann sum go between those extremes. Okay, so if you look at the definition of an upper Riemann sum, still you have a partition, so we'll use the same partition, and they have a sequence of numbers, and these numbers are determined by this formula, and then you look at again the same sum. So what is going on here? So we're talking about the least upper bound of values of the function f. So we're talking about the least upper bound of heights where the x ranges in that interval. So how do you interpret that? So if I'm on this first, this first gap between my partition values, then I'm looking at all values in the range of the function from here to however tall this thing gets, which is up to here. So I'm looking at that range. Now the yi I pick, I guess it goes up to here, sorry. The yi I pick, they say it's the least upper bound. So in other words, it's the greatest value. So in this case, if I'm looking at the upper Riemann sum, maybe I'll use green for that. Maybe I should use red because a stoplight goes red, yellow, green. So maybe I'll pick red for this. I pick the highest value that function attains on this first interval. And that's right here in this case. And so I make my rectangle for my upper Riemann sum, this thing, this big one. Again, it's the same width, but it's just a little bit taller in this case. Okay, so we always want to pick the biggest. Now the second one, it's just slightly taller. Okay, because the biggest value was because of the thickness of the marker. It's kind of hard to distinguish. But the second one, the second upper Riemann sum is like this. The third one is where we have a big drastic change. So on here, if I look at the heights of this function between these 2 points, I see that the height is right here. It's way higher than the one we had picked sort of randomly. So, okay, we will draw that, no problem. We'll get this nice rectangle here. And then over here, again, what's the highest point? Is it here or here? I think they're about the same. So we will draw that in as well. And there we go. The area of the red rectangles is going to be the what's called upper Riemann sum of the function over that partition. So again, the partition was really important. If I had cut this partition in half, so instead of T3 being here, if I put T3 right here, then, between this point and this point, if this was my new T3, I would have, a different maximum height for my upper rectangle. So this is very, very dependent on the partition that you're picking, okay? And that's important because, in fact, what's going to happen to define integration is we're going to sort of do something over all of these partitions, okay? Now, another similar definition is the lower Riemann sum. It's just like the upper Riemann sum, except you pick the lowest height of the function for the rectangle. So in the first subinterval of the partition, first subinterval determined by the partition, instead of picking this upper point or some point in the middle, we'll pick the lowest that function goes. So the lower Riemann sum is down here. So this thing, I'm going to regret putting these L's in here, but that rectangle there is the rectangle for the lower Riemann sum. Now on this interval, this is not the lowest point that the function takes. The lowest point is right here. So this thing is going to be the rectangle for my lower Riemann sum here. So here's my rectangle for the lower. On the next subinterval, this function goes all the way down to here, and that's going to be the height we take for our lower Riemann sum. So there it is. And then finally on the last bit, the lowest value the function takes is right here. And or no, this looks like it's lower. We'll just kind of ignore that and go on with it. So that's our lower Riemann sum. So you can see if I started putting R's in or U's in for the upper Riemann sum, that thing bleeds into these lower Riemann sum rectangles, but it's an overestimate. While the lower Riemann sum is a definite underestimate of things, and the original Riemann sum I made is somewhere in between. Okay, so the red is the upper Riemann sum, the green is the lower, and the black is just a regular Riemann sum sort of in between somewhere. And you can see that the area under the red rectangles is strictly bigger than the area below the green rectangles. And the area under the black rectangles, I guess that's here, 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 and here, is sort of between in some way. Okay, so that's what we mean by Riemann sums. You have a partition, and then you know whether you're doing upper, lower, or regular, it depends. So they define this notation. If you have an interval in a partition already, then UP and LP denote the upper and lower Riemann sums. So we get some problem that I will solve for you, and then a bunch of theorems. Okay, you can read those. Some of you they're going to be assigned to you already. And then we have this next definition. So we finally can define integration in terms of these Riemann sums. Now this definition, there's lots of ways to define integration. In Calc 1, you sort of took a limit as the width of rectangles go to 0, at least that's the common thing to do. And that sort of became the limit because the width gets smaller. We're going to do sort of the same thing here, but in a a more advanced sense. So let's look at definition 44. So if I have a bounded function, so that's a big thing in Riemann integration, that your function's bounded. There are other notions of integration, including what's called Lebesgue integration, that allows unbounded functions, and also improper Riemann integration also allows unbounded functions. But it's there's a lot of subtlety involved in different kinds of integration. Lebesgue is the best, and then from there you can generalize it and so on. But Lebesgue is like the adult version of integration. Riemann is like the kindergartner version of integration, and but we need to start somewhere to be formal. So we start with a bounded function. The domain's a closed interval, so you think about all the integrals you've ever computed that go from some number to some number. Okay, then we say the upper integral from a to b of f is the greatest lower bound of the set of all upper Riemann sums. Now, go back to that definition of upper Riemann sum. The Riemann sum is the value of that area. Okay, the Riemann sum is not the construction you're seeing. It's what you get when you add up width times height, width times height, width times height, width times height, add them all up. That's some number that you get. So what you're doing is you're saying, okay, I'm going to make a partition. I'm going to make the upper Riemann sum. I'm going to write that number down. Then you're going to make another partition. You're going to make a Riemann sum. You're going to write that number down. And you're going to have this big point set, this big collection of numbers. Now that number, that big collection, has an upper bound. How do you know that? Well, if you took if I took this same function and I made a partition that's, the simplest partition I could ever make. Do I have another color? Maybe I don't. I have this blue here. Okay. If I make the most simple partition I ever could, so these are all among the same partition, but if I made a partition just from this point, blue does not work. Maybe I have purple. Okay. So if I made a partition only with these two values, okay, T0, and I'd call that T1, well, then the upper Riemann sum would start at this height, and that would be it, right? There would be nothing else, breaking my rectangles up, okay? Because that would be my only points. I'd have one single interval. Now, that thing is a upper bound of all upper Riemann sums. So on a bounded interval with a bounded function, you're always going to have an upper bound to your Riemann sums. Well, completeness axiom guarantees that there's either a rightmost point or a first point to the right of your collection of upper Riemann sums over, when you make all of them for all partitions. That was freaky. Can you hear this? So this toy of my toddler just turned on its own. There's a ghost here. It's the ghost of Riemann. But anyway, so this purple rectangle is an upper bound if I'm thinking about, all possible partitions. So, we can't make things infinitely large by picking partitions. They're always going to be smaller than this big rectangle. So when we look at this definition of upper integral, it's the greatest lower bound of the set of all upper Riemann sums. Let me write this, okay? In sort of set theoretic notation. So, because we all kind of know a little bit of set theoretic notation. So the upper integral, and they use the notation u. Let me switch to a regular marker again. They use the notation u integral a b. They say f. Now they don't write f of x dx or anything like that because it doesn't matter. It's a geometric sort of concept. It's just this interval sort of defined there, and so on. Now, notice I haven't picked a partition for this, and that's because in the definition of the upper integral, it is the greatest lower bound. So it's the greatest lower bound of all upper Riemann sums. So it's the greatest lower bound of the set of upper Riemann sums. Let's call that maybe R, where R is an upper Riemann sum. That's this construction where we always pick the maximum over some partition T0 through Tn. Now, we saw on this previous sheet that, depending on the partition, if I had this partition with two elements, then I'll just get this one big rectangle, and that's going to be the biggest these numbers can be. But if I had this partition with the original one from T0 to T4, then my upper Riemann sum was the red. And that would be another number in this collection that we're talking about here, this set of numbers. Well, because that set of numbers is bounded above, that thing exists. Okay, this is a number. This exists by the completeness axiom. They call it CA in the book. So we have a similar notion for a lower integral. So we have L integral AB F, and that's the least upper bound. Is it the least upper bound? Yeah, it's the least upper bound of the set of R, where R is a lower Riemann sum over, the partition T0 through Tn. So we're they might say in some class that they're souping over all partitions, and what that means is we form the collection of all partitions, then we compute the lower Riemann sum of every single one of them. That gives us a point set that we then can apply the completeness axiom to, and that's what's going on here. So in the previous example, in this purple partition, so we've already computed the lower bound on this one with the green. If I maybe I need another color. If I tried the same with maybe this yellow, you can see. Let's see. You can see it well enough. If I compute the so with the partition T0, T1, T2, T3, T4, the lower Riemann sum was these green rectangles. If I took just the purple partition, then I have one single rectangle, and its height would be determined by the minimum value of the function over that entire range. Well, that's right here. So if I wanted to find, sort of the lowest that an integral could be, well, it would be the area of that yellow rectangle there. And that would be sort of a lower bound of everything. And just like how the completeness axiom guarantees that every point set bounded above has a rightmost point or a first point to the right, in other words, it has a supremum, then it also means the same thing going left. So the same thing is happening. So that is the definition of an upper Riemann sum and a lower Riemann sum. It's a very non-constructive kind of definition. So, you're never going to list all partitions of an interval. This is impossible to list, not only because there's infinitely many, but it's actually uncountable. So it's an extremely not possible to list, but it suffices as a definition. So what is an integral? Well, in Calc 1 they take this limit of the widths of things, but in analysis, because we don't always have equally spaced partitions, we take this as our definition. So we say that the function, we say if f is bounded on the domain AB, then we say that f is Riemann integrable on AB, say a bounded f, is Riemann integrable on AB if and only if the upper integral of f is equal to the lower integral of f. And if they're equal, then we say, well, that's the integral from a to b of f without an L or a U in the front. Now again, we're not writing of x dx. That's just artifacts of of Calc 2. In that case, if you write the of x dx, you're kind of you're doing what's called choosing a measure, and we don't really care about that, geometrically, because it's still just area under the curve. So that's called the Riemann integral. Now, that's the definition of integral. So when you're doing problems here, you're not going to be computing, antiderivatives and finding, bounds and stuff. We don't have that notion here. We just have these definitions. So let's move on. So definition 46 is the notion of a refinement. Now, the point of refinement works maybe the way you would think it does. So it says a refinement, one partition is a refinement of another. So, is that going the right way? Refinement? Interval is a refinement of the partition, means it's a subset. Ah, yes, that is going the right way. So if I have some interval, AB, here's AB, and I have some partition on my interval. So here's T0, here's T1, here's T2, here's T3, maybe here's T4. Now I could have like 30,000 points, who cares? But I have some kind of partition. Now, to be a refinement of that partition means I add more points to it. But I also keep any of the points I have. That's where the subset part of this is coming in. So if I take a new partition, maybe here's W0, maybe here's W1, here's W2, here's W3, maybe I put a W4 in here, here's W5, here's W6, here's W7, here's W8, and here's W9. So we have one partition, P1, let's call it. It's consisting of the points T0 through T4. We have another partition, call it maybe P2, consisting of the points W0 through W9. Okay. Now, because of how I chose it, this P1 is a subset of P2, because every point in P1 is in P2. T0 is called W0 in P2. T1 is called W2. T2 is called W3. T3 is called W5. And T4 is called W9. So that's a subset. And in this case, we say that P1, or P, which one's the refinement? It's the one with more points. So we say that P2 is a refinement of P1. Okay. In other words, you're making it more granular. You're making it, have essentially better accuracy, if you want to think of it in terms of, calculating an integral. If your partition is more refined, you generally have a closer answer to the actual integral, assuming the actual integral exists. So that's the notion of a refinement. they'll use this this kind of theorem. If you have two partitions, then there's a common refinement. This is a something that's used all the time, okay, and especially in undergraduate analysis. Okay, so now we have a notion of increasing. We hadn't even really talked much about increasing yet, so it's nice to see this. So let's look at definition 47. Definition 47, and this is a very college algebra kind of definition. It says a function is increasing if for each pair of points x and y, with x less than y, you have f of x is less than f of y. So you would say, the basic thing in Calc 1, like this is increasing, okay? Because if x is less than y, then you look at the value of the functions. Here's f of x, and here's f of y. F of x is less than f of y. It's lower on the y-axis than f of y. If I had a function, that does something like this, then that violates being increasing, because I could have an x less than y. So maybe here's x, and then here's y. Oh no, let me not do it that way. Let me put x here. Let me put, oh wait a minute. No, that's correct. X here, y here. If I look at f of x, here's f of x, and then here's, this is the height f of y. F of x is in fact greater than f of y here, so it's not increasing. So the important thing there is that this occurs for all pairs of points. So, it's not just one pair of points can determine increasing. It's that it happens for every pair of points. And then we say non-decreasing if you have or equal to in there, okay? You might have heard people say the difference between, there's a difference between positive integers and non-negative integers, right? Non-negative allows 0 in there, okay? And that's all the definitions in this. Oh no, there's one more. And the final definition is something you were taught in low-level calculus. That, so far we've only allowed intervals of this type, and they say, well, if you, put the b at the bottom, you define that notation as pulling a minus out front. That's what it means. And that the interval from a to a is 0, and that's again has to be defined. We don't allow in this book an interval with the same endpoint on it. By definition, that was one of the earliest things we talked about. So that's it for these definitions. I hope this was useful, and I will do some problems and upload them soon.